Lesson 14 is on efficiency. So we already talked about the two laws of thermodynamics. The first law of thermodynamics, energy cannot be created or destroyed, only changed. And the second law of thermodynamics, no process can be 100% efficient. The one thing I'd like to talk about, what we're looking at for lesson 14 is that second law. We talk about efficiency all the time in vehicles, in appliances, in light bulbs even. You've got regular motorcycles that usually run on fuel. That's mostly what we see. Now, I was at a conference last year. This is called a Bramo electric motorcycle. These things are amazing. The big thing about electric cars and electric vehicles was that they weren't as good. They didn't go as fast as regular ones. This motorcycle actually competes in professional motorcycle races, which is unheard of anywhere. This is actually a female motorcycle racer on a Bramo bike at the moment. If you have some free time, might be a cool thing to check out, bramo.com. So like we said, efficiency, we deal more with the second law of thermodynamics. No process can be 100% efficient. Some energy is always lost as thermal energy. So when we're talking about energy in conversions, we talk about three things. Okay, so there's the energy that goes in. That's 100% of what's going into your object, your light bulb. Okay, so your energy input is your initial energy source. And then you have two things that come out of that. You have useful energy and you have wasted energy. The useful energy is the part that we are using. So in this case, we have electrical energy going in and we have light energy coming out. So this is with like a light bulb. Okay, so we have 100 joules of energy going in. 10 joules comes out as light energy, and the rest of those 90 joules are given off as waste. Okay, that's this arrow coming down here. So the wasted energy is energy lost as heat in the conversion process. Another example we can use is a human. Human's input energy is food. Its output energy is its movement, making more cells, doing different bodily functions. But a human, at the very, very maximum, can only be up to 36% efficient. So that means all that extra energy, that 64% of the rest, is all given off as heat. Now that works well for us because we're warm-blooded. Now, for these, it's just kind of a review of energy coming in and going out. But for this one, please identify the input energy, the useful output energy, and the wasted energy in each of the following situations. So for the first, it would be a light bulb. The second, this is an electric kettle. The third picture here is a gas stove. Now, when we talk about efficiency, we can calculate how efficient something is by using the efficiency formula. Efficiency is a measurement of how effectively a machine converts energy input into useful energy output. This is your formula. Percent efficiency equals the useful energy output, so what's coming out of it that we can use, over or divided by the total energy input, so that's everything we put into the system, times 100. Your answer will be a percent, and remember, the output energy must be less than the input energy. If you end up with something that is 100% or more, something's gone a little bit screwy. Okay, your answer is always going to be less than 100% efficient. This is exactly like finding your mark on a test. You have so many questions right out of however many total questions you could have answered, times 100 equals your percent. This is the exact same. So we'll do a couple practice problems. The first one here is a very basic problem. You may see one or two of these on a test. It's very straightforward, only one calculation. A crane lifts a load from the ground to the second floor of a building. The process, the crane does 23,000 joules of work. Okay? And if you keep reading, or mechanical energy input, while doing 8,000 joules of useful work. That's our useful output energy. And what's the efficiency? Remember, it's always the small number divided by the big number times 100. So we write down our formula, and we substitute our numbers in. So we have our formula, percent efficiency equals the output energy divided by your input energy times 100. We substitute our numbers in, 8,000 divided by 23,000 times 100. And we end up with 34.78, which equals 35% efficiency. Now for the second question, You're given the percent efficiency, and you're given the output energy, but we need to know what the input energy is. So we write down our formula, and we substitute our numbers in. Now what we have to do with this is solve it. What I would suggest you do is move your input over to the other side of the equal sign, and then move your 15.0 back equals your rest of your formula. How we're going to do that is right now opposite operations. So 32,000 is divided by your input. The opposite of dividing is multiplying. So we multiply by your input. That gets rid of that one. What we do to one side, we must do to the other. We also have to get rid of your 15. So we're going to divide by 15. So our formula looks like this. So now all you have to do is the math. 32,000 divided by 15 times 100 ends up to be 213,333.3 repeated with significant digits. It's 213,330 joules. Now for our last problem here, this is how probably a question on a test is going to look. You're given some numbers. You're not given your joules right off the bat. And what you have to do is calculate how many joules you have for your input and your output energy, and then do your efficiency calculation. So let's see what we have first. 25 meters is the height. 13 meters per second is the velocity. 68 kilograms is your mass. We have our mass, our gravity, and our height to do our potential energy formula. We have our mass and our velocity, or our speed, to complete the kinetic energy formula. So we're going to find our joules from both of those, and then after that we're going to use that in our efficiency formula. When you're doing these questions, you still need to include the formula, the work, and the answer, but you do not need to round anything yet. Okay, so our potential energy formula, M times G times H, 68 times 9.81 times 25 equals 16,677. For our kinetic energy formula, mass times speed squared divided by 2 ends up to be 68 times 13 squared divided by 2. We end up with 57.46 joules. Now we plug those two numbers into our efficiency formula because that's all we need. If we're trying to figure out what's our input energy and what's our output energy, the top number is our potential energy, so that's what's going into the system. That's how much energy we have at the top of the hill. The kinetic energy on the bottom here is how much energy we had coming out at the bottom of the hill after he sped down on his bike. If you're confused, however, which one is which, you always use the smaller number as your output energy. So our output energy divided by our input energy times 100 is going to equal out in the end 34.45 or 35%. Now you have two questions to do for homework.